Good morning. Till now we have discussed about the various types of vibrations: longitudinal vibrations, transverse vibrations, free vibrations and force vibrations. Today we are going to discuss two important terms named as magnification factor and transmissibility, which is applicable for even it is for free vibration or a force vibration, but very specific for force vibration. So in force vibration we have seen there are two types of vibrations. One is damped vibration and another one is a undamped vibration. The difference between a damped vibration and undamped vibration is, in damped vibration there is some amount of external resistance which resists the motion of the vibrating body. So in undamped vibration there is no external resistance which controls the movement of the vibration of the body. So now let us see what is the significance of this magnification factor and transmissibility, how we can analyze the magnification factor and transmissibility with respect to their frequency ratios, that is omega by omega n, and what the damping coefficient will control the magnification factor and transmissibility, and what the phase angle will influence the parameters of these quantities. These things we will discuss. These are very, very important for the practical purpose and to install your equipment or to run your equipment with safe mode, and the equipment should not disturb the surrounding equipment so that the entire system will run in a smooth manner. We have to take care about certain things. Those are governed by these magnification factor and transmissibility. So let us see how we define these terms magnification factor. So as I said, this is applicable for mainly for force vibrations, okay? And how we define a magnification factor? It is a ratio. So it is defined as the ratio of the amplitude of steady state response to the static deflection under the action of force. So here we are comparing the amplitude of the vibration and the displacement of the corresponding force if you give it in a static mode. Let us take a simple example like this. A force of like 100 Newton is applied on a body without any dynamic action, okay? Then you get some amount of deflection or some amount of deformation or some physical changes that happens in the member. Suppose if the same force, instead of applying statically, if you apply dynamically, then can you get the similar effects or will you get some effects other than the previous one? If it is the case, so how it varies depends upon this dynamic nature and what factors that controls that dynamic nature of the object, isn't it? So that is studied in magnification factor. So you can see it is defined as the ratio. It is defined as the ratio of the amplitude of the steady state response to static deflection under the action of force. So the force is F. I take the force is F. So I said it is F naught. Okay. So this force is applied under dynamic condition. So then it vibrates and it gives a vibrating signal, and once the vibration states a steady state, isn't it? After a certain amount of time, the vibration reaches to steady state, and at that steady state, so its response is given by an amplitude, that is the maximum amount of displacement that is obtained due to the vibration, isn't it? So that is given by amplitude here. It is given by root of s minus omega square whole square plus c omega whole square. So what is the omega, what is s? Of course, earlier I used the stiffness K is used as a stiffness, and here I have written the same stiffness word as S. So stiffness is represented by S. So this is the stiffness. Okay, omega is the excitation frequency. So that is applied frequency. So that is omega is external frequency or excitation frequency. Or applied frequency, excitation frequency. Okay, so here you can see what is it is the f naught by root of s minus omega square whole square plus c omega whole square. So f naught is the applied force, okay, and s or k is the stiffness, omega is the excitation frequency. So you can see the steady state vibration which gives an amplitude. The amplitude is given by this. So the first term f naught by root over s minus omega square whole square plus c omega whole square. So f naught is the applied force, s is the spring stiffness, omega is the excitation frequency or the applied frequency, c is the damping, isn't it? So this gives the amplitude of the vibration under the steady state response. And then if the same force of f naught, if I apply on that system by assuming it is not dynamic in nature, it is steady state, then I get the deflection of that is given by simply f naught by s. So this is the vibration and its corresponding amplitude when you apply a force of f naught, and this is the deflection or a deformation if the same force is applied without under vibrating mode, which is a static mode, isn't it? So the ratio which you get here, f naught get cancelled, then you can see this s will go into numerator, then s by root of s minus m omega square whole square plus c omega whole square. Then I can rearrange these terms as per my requirement in terms of omega and omega n. So divide the entire equation by both numerator and denominator. Divide the equation numerator and denominator by s. Numerator and denominator by s. Then dividing it, s by s is 1. Then s here you can see s by s minus m omega square by s whole square plus c by s omega square. Okay. Then s by s is 1, isn't it? So actually I am dividing it by s. Okay, both numerator and denominator. So here inside there is a square term is there and outside there is a root is there. Simply it goes like an s. Then 1 here s by s 1 minus m by s omega square plus c by s omega square. And we know that the basic fundamental, we know that omega n is equal to s by m. That is omega n is equal to root s by m. Okay, so if I write in that way, m by s is 1 by omega n. So 1 by omega n is, okay, root m by k or m by s. And here square is there. So omega 1 by omega n square is equal to m by s. So I can replace it here m by s by 1 by omega n, and already there is a square here. Okay, so omega square is there, m by s is 1 by omega n square. So 1 by omega n square as written here, then omega square by omega n square, we can take it as a whole square. Then square root of 1 minus omega by omega n square whole square plus c by s, okay, into omega. We know that c by s is also can be written as 2 zeta by omega n. This is from the earlier concepts which we have obtained in damped vibration. We have seen the c by s is equal to 2 zeta by omega n. Okay, that is replaced here. So ultimately I got the equation in terms of the natural frequency and the applied frequency. You can see in the final equation of omega m magnification factor, we have only the terms related to the frequencies, that is excitation frequency and natural frequency, and the damping is a term. So we can say that the magnification factor is a function of frequency ratio and damping factor zeta. So that is what you can see here. So we can draw the diagram for the analysis part what we have seen in a graphical form. So just now I said magnification factor depends on the ratio of frequencies as well as the damping factor. What is this ratio of frequency? Omega by omega n. What is this damping factor? Zeta. Let us see here the magnification versus frequency ratio curve. This is magnification. What is the unit for magnification? So it is a ratio. So magnification factor is a ratio. So ratio will never have a unit. So here we have compared the displacements obtained under forced vibration under steady state of the same force. So it is the ratio of the displacements. So then it doesn't have any unit. It is simply a dimensionless number like 1, 2, 3, 4. And then the x-axis we will plot a graph that is omega by omega n. Omega is the applied frequency, omega n is the natural frequency of the system. So omega by omega n is also a dimensionless. So both x-axis and y-axis is a dimensionless numbers. You can plot the graph to get the behavior of this magnification factor with respect to various frequencies under different damping factors. So you can see here the phenomena, it goes like this. This zeta 0, that is no damping. Then further damping is provided like 0.1, 0.2, 0.3, 0.4. All these are under damping cases. Under damping. We know that there are three cases: under damping, over damping, and critical damping. We have discussed these things in damped vibration lecture, under damping, over damping and critical damping. So when we call under damping, when we call over damping like this, if zeta is less than 1, we call under damping. If zeta is equal to 1, we call it as a critical damping. And if zeta is greater than 1, over damping. So you can see here the different zeta values like 0 to 0.1, 0.2, 0.3, 0.4, so on 1. That means all of these curves are representing an under damping case. And this is a critical damping, and further you can see the over damping. So let us see the first here for a zeta value of 0. Zeta value of 0, that means there is no damping is given. There is no damping is given. So omega by omega n as it increases. So omega by omega n, say it is increasing, and if it is like 1 or greater than 1 like this. You can see here as omega by omega n is increasing, the magnification factor is enormously increasing. So zeta 0, it is an under damping case because it is less than 1. So omega by omega n is up to 1. You can see the magnification factor continuously increasing. So what is magnification factor? Just now we defined. So it is the ratio of the amplitude of the vibration and the same force if you apply a static, so I can write it as a delta. So amplitude of vibration A, that is vibration amplitude, and static deflection of delta. So if you look at here more value, that means this is say 3 or 4 like this. That means A is equal to 3 times of delta or 4 times of delta like this. That means if you provide very less amount of damping, or if you don't provide the damping, then the damped vibration will have much effect on the displacements. That is like the amplitude may be 3 times of static deflection or 4 times of the deflection. That means the body will undergo a vibration with more amount of the amplitude. That is why we have to see that your system is better to run the omega by omega n is greater than 1, because when it is greater than 1, you can see the values of this magnification factor is dropping. It is going to be down. So I can say one thing. Suppose if I don't have a damping, then it is always preferred to run the equipment omega by omega n is greater than 1. And similar, if I provide some amount of damping, that is like 0.1, 0.2, 0.3, 0.4, some amount of the damping is provided. When I provide the damping, automatically my magnification factor is decreasing. That means this amplitude under the damped vibration will be reduced something like 2 times, 1 time like that. And as you proceed omega by omega n, more and more values, okay, then the zeta, even though it is 0, then the magnification factor will be less than 1. That means what you can understand is, so at higher speeds, what is omega by omega n? So when omega is greater than omega n, that means the applied frequency or an external frequency is more and more than the natural frequency of the system, then your omega by omega n is more and more value. So in that case, you can see the magnification factor is decreasing. So like 0.1, 0.2, 0.3, 0.4 like that. And there is a one situation where you can see when the damping factor is 1, okay, then almost you never reach this magnification factor more than 1. What it indicates, if you provide more and more amount of the damping, then automatically the vibration displacement is less than the static deflection, isn't it? So that is why you are preferred to run or to operate with more damping, isn't it? So whereas you can see once omega by omega n is approximately around 2 irrespective of zeta, so zeta is not influencing. So all the curves reached at a line. You can see all of them have reached to at a single line. So that means if you provide the applied frequency, or if your equipment is running at high frequency compared to its natural frequency, it is immaterial how much damping you are providing. So it is only bothering between omega by omega n is less than 2. That means when you are running your equipment at a lower speeds with respect to its natural frequency, then only the zeta will influence. Okay? And similar, this is the phase angle versus frequency ratio. How we have written here the magnification versus omega by omega n. Here we have written the other part, that is omega by omega n versus phase angle with respect to zeta. So you can see here also the values of zeta is increasing, okay, 0, like 0.1, 0.2, 0.5, like 1. So these values, you can see zeta 0 is like a straight line. Zeta 0.1, zeta 0.1, then zeta 0.2, zeta 0.5, like zeta is 1. So once you see at higher frequencies, that is omega by omega n is around 2, like that, zeta is not influencing anything either in the phase angle or in the magnification factor. So the critical thing is entire system when you are operating when omega by omega n is less than 2, and whereas here you can see all of them are reaching a point where omega by omega n is 1. So irrespective of zeta value, the phase angle for everything is same, which is 90 degrees, isn't it? So this is what a magnification factor is concerned. Then the other important term is vibration isolation and transmissibility. Vibration isolation and transmissibility. So this is one of the important parameter, especially when you are installing machines in a machine lab, or even if you are installing an equipment in a factory, okay, and you should take care about what are the factors that is governed by one machine to the other machine, isn't it? It is as simple as like this. One classroom is there, and that class consists of a number of people with different backgrounds, that may be social backgrounds, economical backgrounds, academic backgrounds, and all of this. So suppose if you assume that class consists of 5 people with good academic background and very decent in nature, and let us assume there are another 5 in the same class, so with very poor academic background, I am talking about academic background and their behavior, and they don't have a particular proper mannerisms. And there are some people, a mixed mode, like they have a moderate type of academic behavior as well as moderate behavior of a personal behavior. So when you combine all of them in a classroom, okay, if you don't take any precautions, then it may happen sometimes the good people may get damaged in the sense they will also become bad, or a bad people usually they will not become good, because unless you take proper care. So here let us say there is a factory where there are 5-6 equipment are available. One is a compressor, like one is a compressor, and another one is an IC engine, and another one is a blower, another one is like a generator, and there is one more machine which is used for a specific purpose of that particular factory. So we are not guaranteed that all these equipment will run at same time, and at the same time we are not sure that all the equipment will run at the same speed, because one equipment requires one speed to operate and another equipment run another speed. And all the equipment are not having the same mass and they don't have the same elastic nature, isn't it? So, but we cannot separate them one mission to the other mission. So we have to keep all these machines in the same room. Like in the classroom where there are n number of people, we cannot compartment provided, or we cannot distinguish, or we cannot separate X to Y, Y to Z. We should have certain mechanism. Similar here, there are n number of equipment with the different masses and they run with the different speeds and a different time. So if one of the machine is running and it is producing a large amount of vibrations, isn't it? And there is another machine running in the same office or same industry, okay, which is running with very smooth in style. One is disturbing large and another one is running very smooth. Suppose if you don't take any care, then what will happen? The safe running and a good running equipment also get spoiled by its neighboring equipment, because which is generating vibrations and these vibrations are going to be transmitted to them, then it causes the damage. So that case we have to take care about how to isolate your equipment, isn't it? And how to transmit your vibrations smoothly to the ground without hampering its neighboring equipment. That is a very big issue when you are dealing with large size equipment which is running. So that we can say here, vibration, isolation and transmissibility. That means my first objective is to isolate the vibration. If I cannot isolate the vibration, then I can go for a better mechanism for transmissibility, isn't it? So first thing, isolation. If possible, we go for isolation. If not possible, we can go for the transmissibility. So how the transmissibility is defined? It is also a ratio like a magnification factor. So it is force transmitted to the foundation to the force applied. So this transmissibility is represented by a letter called epsilon, which is nothing but Ft by F naught. What is Ft? What is F naught? So Ft is force transmitted to the foundation. So the amount of vibration which generates the force that is transmitted to the foundation, and F naught is force applied. Force transmitted and force applied. So in the other way, it gives an idea about the effectiveness of the vibration isolating material. You are well aware of seeing in general when you are installing some equipment, we don't keep the equipment on the ground directly. So recall in your machine drawing which you have studied foundation boards, and there you have seen the heavy equipment is placed on the ground by placing various foundation boards, by providing like concrete and providing some isolating material, rubber pads, gaskets and all these things, so that the vibration which is generated from the equipment will transmit to the ground in a smooth way. So here what I said, the transmissibility is a ratio which is nothing but force transmitted to the foundation by force applied. So this is transmitted force and this is applied force. So it's a ratio, a dimensionless number. So we have seen in the earlier, in a force damped vibration, we have written what is force transmitted and what is force applied. So in terms of zeta and omega. So force transmitted is given by root of 1 plus 2 zeta omega by omega n whole square, and force applied is root of 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square, isn't it? So there are two special cases which we will discuss separately. That is, one is at resonance and another one is if you don't use a damper. So what is resonance? When your external frequency matches with your natural frequency, or omega by omega n is equal to 1. This is what we call a resonance case. That is, applied frequency and natural frequency, if both are matching, that is omega by omega n is 1. So wherever here omega by omega n term is there, you replace them as a 1. So this is 1 plus 2 zeta into 1, 2 zeta square. Then here omega by omega n is 1, 1 minus 1 whole square. It is 0, 0 square 0. That's why I have not written anything here. 0 plus. Then 2 zeta omega by omega n 1. So 2 zeta whole square under root. Take out the root. Then it gives simply. So epsilon is root over 1 plus 2 zeta whole square by 2 zeta. That means at resonance, so the transmissibility is function of only zeta. Of course, we will see a graphical representation of same what we are discussing. Then the second one, when you don't use a damper. So if you don't use a damper, then it is a free vibration where zeta is equal to 0. No damper is used. There is no damper. That means it is simply a forced vibration, forced undamped vibration. We can call it as a forced undamped vibration. In that case, you write zeta as 0. Okay, then if you write this is 0, then whatever your omega and omega n, it is immaterial. 0 into something is 0, then 1. Then here, this term also becomes 0. Then here 1 minus omega by omega n square whole square. So whole square, if you take it out, then root will be taken out. Then it becomes epsilon is equal to 1 by 1 minus omega by omega n whole square. This is no damper is used. So the two cases which we have taken as special cases, one is a resonance case where external frequency matches with the natural frequency. That is the case 1. Where epsilon is equal to root over 1. And the second one, when you don't use a damper, so automatically that is called free vibration, that is forced undamped vibration, where your epsilon will be 1 by root 1 plus or minus 1 minus omega by omega n whole square. So this you can convert in a graphical form, which gives a lot of information. What is that information? How we can conclude by seeing this curve with respect to zeta, let us see. Like in the magnification factor, we have drawn a curve between magnification factor and omega by omega n with respect to zeta. Here also we can write the transmissibility versus frequency ratio, that is omega by omega n with respect to zeta. So zeta 0, zeta like 0.2, 0.3, 0.4, so on. If you draw this, you can see, so omega by omega n less than 1, less than 1. So when omega by omega n is less than 1, so for the values of zeta is greater than 0. So for all of them, your epsilon is goes on increasing, and like 2 or 3 or 4, it is a function of your zeta. So epsilon is 2, 3, 4 means what is it? Epsilon, we have defined Ft by F naught. That is force transmitted to the foundation to the force applied. That means the static force, the force which you apply and the force which it is transmitted to the foundation is more and more. That is why at lower speeds, at lower speeds, the force transmitted to the foundation is high, and if the zeta value is less, then it is still high. Whereas if you go beyond 1, then it is going to be decrease. So like the zeta value is C 0.2, 0.5 like this. When omega by omega n is root 2, omega by omega n is root 2. So the zeta is not influencing anything. No influence, irrespective of your zeta 0, 0.2, 0.5, 0.6, whatever it may be, your epsilon is simply 1. That means what it indicates, Ft is equal to F naught. So that is force transmitted to the foundation is equal to force applied. So that is also not preferred. What is my objective? My objective is the vibration of a particular mission should not damage the surrounding equipment, or it should not cause any severe effects into its surroundings. So when it is possible, if I go for like omega by omega n greater than root 2, then you can see my epsilon value is always less than 1. If I go omega by omega n more and more than root 2, my epsilon value is less than 1. And you can also see when you see the other way, when the epsilon, when the omega by omega n is more and more value, when zeta even lesser value, zeta lesser value, your epsilon is less. You can see the curve, how it goes. The curve goes like the curves are moving in this fashion. So as the omega by omega n is increasing more and more, for a lower value of the zeta, epsilon will be lower. That means at a higher external frequency compared to the natural frequency, zeta value, even a lesser value, you have a beneficiaries for the system. But one thing you keep into your mind, you cannot run your equipment from beginning 0 to this speed without skipping anything. So this should pass the entire speeds of like this, then only it reaches to this particular speed. So you can cover this area in a lesser time and you can run the equipment more in this time, so that your equipment will be safe in mode. That is why you can see majority of the equipment, when they run at a lower speed, then they vibrate, then they give us noise, then it gives some trouble. If the same thing, if it runs at very high speed, then they will be operating in a very smooth manner. Recall, in your home a fan is running. You might have observed many of the times when I put the fan at a lower speed, the fan is like vibrating, or the fan is giving a humming sound, or fan is giving some vibration. But once you increase the speed certain extent, this further increases. Then if you go beyond that, then you will find a phenomena where there is a smooth operation. So of course, like the transmissibility and magnification factors, you might have seen when omega by omega n is greater than 1, then both the transmissibility, okay, and this magnification factor, both are lesser than 1. That means it gives a suggestion higher speeds with respect to its natural frequencies will run the equipment in a smooth manner, either giving the forces to the foundation or giving the displacements to the foundation or its surroundings very less. But keep in mind, if you want to come to this state, you have to pass this. This is as simple as like you are aware of one simple proverb, okay? So earning up to certain extent will leads to a tedious work and tedious hard work. Beyond that, the rupee which you earned will earn its own automatically, isn't it? But to gain up to certain amount of money or certain amount of wealth, you have to work like a machine. Once you reach that state, then the machine will take care about it. That is what you can recall break-even point in your engineering application. So at the beginning of a firm, till it break-evens, the profits will not occur. It will be in losses. Once you cross your break-even, then your profits will come like enormous quantities and you will be in a limelight. Similar, even the nature under the vibrations also will behave like the same manner. So these two factors, vibration isolation and transmissibility, are very, very important, a practical point of view, and these are used to installation purpose and these are used to control the surrounding equipment. So in one of the lecture, that is in one lecture, we will see the problems based upon the background what we have studied, that is transmissibility and the magnification factor. So once you solve the problem, then you will easily identify the background what we have discussed, how it can be useful for a analysis of a vibrating body under free, under forced, under damped, undamped. Okay, all these cases can be easily studied and can strengthen your knowledge by solving a problem and comparing the analytical data to a practical data. Okay, thank you.